Okay, so I'm very, very happy today to very briefly introduce Zhongwei Zhao. Zhongwei has been here for about 4 years initially as a postdoc researcher, and now just about to become research faculty. And the work he's doing has been actually, I think it's really extremely interesting and important. As he'll tell you, early detection of cancer seems the best way to save an enormous amount of lives. And CT scans are one way that you can good chance you can do it by using AI algorithms. And so over the last few years, we're getting some extremely good results on this. The problem is complex because it requires, on the AI side, it requires understanding and mastery of a whole lot of different types of AI algorithms, and and creating new ones involving vision, involving language, and I guess reasoning is going to come in here soon as well. On the other side, this work is no use unless the radiologists, the people who are actually going to use these systems, know about it, understand it, and that they're that we're solving problems that they actually care about and could use. And another complication is getting data. AI feeds on data. Medical data is complex to get hold of. And many people can testify to that, some in this room, I think. And so one aspect of the work is actually also reaching out to people and getting people who have the data and have it organized and enough so that it can be made AI friendly. And we've had some slightly disappointing experiences with that in the past, but we've actually got some, thanks to Zhongwei, there were some excellent collaborators now. So Zhongwei's work, I'd say, before coming here, he was at Arizona State University, where he did extremely well, won prizes. His work here has been very successful. I mean, I've seen the slides. He's giving you the high-level picture of everything he's doing. There's a lot of technical work underlying here. There's a whole lot of technical papers and AI conferences and things published in the radiology abstracts, big companies. So it's aiming to hit the AI and the radiologists. Maybe that's enough. And now away. The space is yours. Yeah. Jason, you're delegated to ask questions if you feel inspired to do so.
Frequently happens.
Not unknown.
Yeah. Thank you very much for coming today, and good morning, everyone. I'm Zhongwei Zhou. So 2021 and 2025 is both a big year to me, and I joined Hopkins 2021, and now this year I get my first NIH grant. Trying really hard, and I get a really great training at Johns Hopkins University. I first do the project, then lead the project. Now I try to design the program for many people to collaborate. So this talk, I will just summarize what a lot of the research topics that I have been doing for the last 4 years at Hopkins. The goal is to detect cancer earlier. Cancer is the second killer in the US and in the worldwide. And detect the cancer early is not easy for both human or for the human radiologist or for the AI. So there is a benefit to detect very early. Of course, you save a lot of life because you can treat it earlier, and the survival rate will go higher. CT is not the only one to do the early detection. You have a whole bunch of other ways, but CT is a very cheap one and a widely adopted one. So there are more than 80,000 CT scans taken every year in the US. So it has the potential for us to detect cancer. But from CT itself, radiologists didn't do very well in detecting early cancer. So the study shows the radiologist may only have a 30 to 40% sensitivity to detect this. And this motivates us to see if AI can help in this manner using computer vision algorithm to detect the small tumor less than 2 centimeters from the CT and even earlier if the cancer is not that visible at that stage. A successful story is about detecting cancer in the pancreas. So I joined Hopkins and I really luckily to join the Felix project. The goal is to find the pancreas in the CT and detect the cancer as early as possible. So we formulated this problem as a semantic segmentation. We trained the AI algorithm to classify every voxel in the three-dimensional CT as a healthy organ and a tumor and background. So the result very promising and exciting. We compare with the expert radiologists at Hopkins and everywhere in the country. So as said, for the small cancer, the sensitivity is extremely low. And our AI can achieve 94% sensitivity in detecting this. And even for the detected all size cancer, radiologists the performance range in 70 to 90%. And we can achieve 97, and with the more current AI, we can achieve 99 even. And specificity also outperform radiologists. So here's an example how AI can actually be implemented and help radiologists to detect earlier. So the patient have the cancer and probably it's already very late when the radiologist detect it. And our AI can also detect and segment its boundary. And actually 8 months earlier, if we trace back the CT scan, our AI is able to detect and localize this small cancer as well, where the radiologist missed at that point. And we have a lot of this kind of example to show the AI can detect earlier cancer around 6 months earlier than expert radiologists.
And you get your training data for that by waiting for a later diagnosis? And then say, could we have, so you know that this thing is going to turn out to be cancer because it's
a longitudinal data curation. So we know this patient have the cancer later, then we pick up the early scan.
Well, that's for testing, the training he'll get into as well.
No, what I mean is in order to get supervision for early cancer
Oh, we
detection.
don't have a supervision because this need a human annotation. If a human miss it, we cannot use for training. So we train the AI on the bigger tumor and then test on the small tumor and it turns out it can detect something there.
But I think a lot of the point, and it will come up here, is how to get supervision without humans making the supervision, and he'll be addressing that in several ways.
Let me make an analogy. You find out if somebody has Alzheimer's after they die and you do the autopsy.
Yeah.
You can use that as a supervision signal to detect it while they're still alive.
A very weak supervision.
Why?
Well, because it gives you very little information. What you'd really like to detect Alzheimer's to get the studies of brain activity, whatever diagnosis it could be beforehand, to see, and that type of. But I think maybe I'll say as somebody who knows what's going on here, I'll say come back to that in a bit because I think some of those issues will be addressed.
Okay.
Yeah. There's quite a lot of material to get through, and I think that would be.
Okay.
So why is this so difficult? Computer vision do this every day, right? You're supposed to have a very strong AI algorithm to do this task. But the difference is computer vision algorithm, they are tested mostly on the natural image. And you see the natural image, the data set curation also a big problem. Usually the object in the middle or object very visible in the image. But in medical it's different. First, the data is a whole body data, it's a three-dimensional. If you count the pixel, the foreground pixel that you are interested in this image, only 0.0001% is what you really interested. So that makes it difficult for AI algorithm to directly apply to this problem. And another challenge is we do not have enough data to train this as said. Annotating is really costly and require human expert. It's not like an image that you can download from a website, you can annotate by student and so on. So we don't have enough AI-ready data to train this kind of advanced computer vision algorithms. So by AI-ready, I hear is talk about voxel-wise annotation, because you want not only to detect it, you want to localize and also measure the size. So the data, the suitable training data should be voxel-wise annotation. So the Felix project has been really successful, but if you think about it, it's to prepare this kind of AI-ready data set, we calculate it's estimated we need a 25-person year to create such a huge database to be able to have a strong AI help radiologists. So scaling this effort to more type of cancer will be a problematic thing. So the key question I try to figure out is where to get this data and how to annotate this data, and to make sure the AI is generalizable to multiple hospitals, how to collect the data from different hospitals for both training or validation. And then after all this, we try to figure out which AI algorithm to use and to improve them, either vision or language or vision language algorithm. And then lastly, probably most important, can this AI really help radiologists in their practice, clinical practice? So this talk will have a 4 chapter. First, let's say we have already curated a very suitable data set, per voxel annotated data set, how to develop a very strong algorithm to solve this problem. And realistically, for different type of cancer, we may not have this data set. Then second, how we able to efficiently create such per voxel annotation to solve different problems. And then we move on to the novel strategy. If we can further reduce the need of a voxel annotation, for example, we can use some foundation model to reduce the need. We can use the radiology report. It's already ready in the clinical hospital. And we can even use some synthetic data as the additional training resource. Then lastly, I will have 3 user case how AI we develop can help radiologists to make their more efficient and more and faster and more accurately detect the tumor. First chapter is about segmentation algorithm. So if you follow the computer vision literature, you will see every day you have a very novel algorithm come out. And in medical, I'm really fortunate to contribute a quite impactful algorithm to detect the cancer or to detect other disease. And yeah, of course, the most popular one is UNet. It's not only be used in medical, but also diffusion model everywhere. And I invent one, and then our lab also have a invention to make the transformer incorporate into the UNet. So these are also all very successful architecture. So during my PhD, I invented this UNet++ algorithm. So it's essentially a UNet architecture, but we find the UNet is not necessarily suitable for all type of all size of the tumor size. For example, if you have a shallow UNet, it might be good at detect small stuff because its receptive field is small. And if you have a deeper, probably more suitable for the bigger object like an organ or later stage cancer. We don't know. So in practice, UNet try to figure out what's the best way to do this. And my solution is to let the algorithm to search itself what is the optimal depth to solve this kind of problem. So you can see this is a sort of early version of the neural architecture search to ask it to automatically figure out the best one. So in this case, we found that the UNet++ is very effective. So the performance is pretty strong. And also it's faster because we assembled different type of UNet into one architecture. And in the inference phase, you can customize how much you want to use. So it's much faster than create a different type of UNet. And the UNet++ has inspired many other strong architecture in either medical domain or computer vision domain. There are many independent research groups to show UNet++ not only benefit for different other medical tasks, but also beyond the medicine, like different area. So we have been, after joining Hopkins, I also involved in improving the transformer UNet to solve this problem. And it's all very good. And we developed the algorithm, this kind of a strong algorithm on the JHU data and the test on JHU data. So after I spent the time creating new architecture, more and more I figured out important part is how to evaluate very well. Because I found no matter UNet or transformer UNet, it can perform very well in internal validation. But when you transfer to different hospital, it have a serious problem. I will give you an example. Here is the JHU performance. And we evaluate on 6 different hospitals from different countries. And we found the performance slightly decrease. And in some hospitals, it's decreased a lot. So this problem is pretty common in practical. It's called a domain transfer problem. And this is not really about the architectural design. It's more about you need to figure out something else to be able to ask the AI algorithm to be robust to different domains. So we have, after joining Hopkins, I have think about a way to improve the robustness of the AI algorithm across different domains. So I will introduce more in the later, but our preliminary result is pretty promising. So we are able to make the algorithm not only work for the Hopkins data, but also for the California data, for European data, Chinese data, and so on. And we also initialize a standard benchmark to invite the researcher around the world to think about and to solve this problem, domain transfer problem. So we call it the touchstone benchmark. The key feature of this challenge, different from other open challenge, is we contribute a very big out of distribution test set so that you make sure it's not you create an AI and overfit it again and again in the in-domain data. And we also provide a very large multi-hospital training data set to see if it helps. And this is one of the biggest public data we release. And we also invite the AI inventor to join this effort because they are the best one who want their algorithm to be successful and want to show their algorithm is robust and the long-term investment. So far, CNN-based, transformer-based, and even member-based, we don't want this kind of challenge to be like several months. We want it to encourage more and more architecture to come out. And we are now preparing the second version of the touchstone to make sure the AI algorithm is very robust in cancer detection as well. So that's about the architecture. Once we have enough data to train, we can always invent more architecture and make sure it's robust. Now the question is how to get this AI-ready data if I have a good algorithm. So as said, we proposed some efficient annotation tool. It's called active learning. And this is the biggest, largest annotated public data released by Hopkins. It provides 9,000 patient CT scan with or without cancer. And this CT scan comes from 138 hospitals worldwide. So it's currently still one of the biggest. And how to create this? Why not other people do this? So it's not really feasible to ask a radiologist to annotate all this scan. I will explain why later. And we developed the active learning algorithm that can speed up the organ segmentation and tumor segmentation by 500 times and 80. This is our data set. Look like Apple released. It's a pretty big data set here. And the secret part is active learning. I will describe later. It have a very nice property. And the important part is we create in 3 weeks. This is cannot imagine if you use a conventional annotation method. I will introduce how we do this. Active learning. It's a human in the loop. So you don't want the very busy radiologist to randomly annotate images for you. You want to spend their time wisely and to use some clever way to suggest what they should annotate. So we have a human in the loop, have AI in the loop. We want AI to suggest what they should pay attention. So we have an AI model. We let the model make prediction, pseudo label, and we find the most important image or most important region in this image for the radiologist to revise, and then add to the training data and use this training data to fine tune the AI algorithm, make sure they don't make same mistake again and again, then make the prediction. Then hopefully the radiologist in next stage will have to correct a different type of error. So this is called human in the loop. As you can imagine, the most important part is how to select the best area in the image or how to select the most difficult patient. We have several criteria, and we compute the AI consistency. So basically, we train multiple AI to predict the same patient and see if they agree or not. So even if we don't know the ground truth, we know the AI make a different opinion. So that area might be the most important part for radiologists to review. Uncertainty, AI make prediction with the confidence. So we want to pick up the area that AI feel most uncertain and ask the radiologist to review. The last one is overlap. Overlap means the prior knowledge. We know the organ cannot overlap. So the one pixel cannot belong to liver and the pancreas at the same time. If AI make this mistake, we know this pixel must have some issue, although we don't know what's the ground truth. So consider all these 3 criteria together, we can generate an attention map that highlights the most important area in this patient to and give to the radiologist to review. And we further summarize the taxonomy of the common mistake made by AI algorithm. And the assumption is if the AI can learn from this error and fine tune it here, and in the next stage, it can avoid this kind of error in the rest of the image.
So if I understand right, you have a classifier that classifies each pixel as being liver or not liver, and a separate binary classifier for pancreas and so on for every possible kind of tissue.
Yes.
An alternative would have been to have a multi-way classifier and then look at its entropy and the attention map.
Correct.
Yeah. Why is this way better?
No, I think you're doing the second, if I'm translating the terminology.
Well, the idea of overlap can't happen if you have a multi-way classifier for the pixel. If you can't classify it as both liver and pancreas.
Yes, it can happen. That's why we have this criteria to say when it happens, something must be wrong.
I was explaining why I thought you had several binary classifiers or a multi-label classifier instead of a multi-way, a multi-class classifier.
Because sometimes semantic segmentation would be multi-class, I think.
But then it can't give overlap.
Sometimes it can have an overlap. For example, we want to segment the vein in the liver and the liver itself. So they are overlapping. So one pixel can correspond to vein in the liver and also the liver. So you cannot treat it as a multi-class.
Yeah, so you're saying that the output is not a one hot vector, it can be a multi-hot vector.
Yes.
So it is not multi-class.
Yeah, correct. Question.
Can't you literally have both in a single voxel? Like if
It's
there's,
happened a lot.
That's what you're saying.
Yeah,
Okay, you mean because the voxel is like divided, it's at the
yeah,
edge?
well, there's like a certain granularity. You
Yeah,
have
yeah,
pretty
sure.
big voxels that might
Yeah.
have like
And sometimes the organ boundary is blurry. For example, we get older, the organ boundary become blurry. You don't know this is really belong to which organ.
Yeah, voxels are pretty big in terms of what you squeeze them and,
How big are they?
it's, you know,
A few centimeters.
Oh, that's quite big. Okay.
So couldn't it be?
not centimeter, sorry,
No.
Oh, sorry, millimeters.
Okay. Still pretty big.
It's
in terms
yeah.
of cells and stuff like
Yeah.
that, it's huge.
So you wouldn't consider it an error if there is actually both of the same, it's just when it has quite a boundary that there's like an issue with overlap.
Yeah, the most challenging part in this segmentation is boundary, because in the middle, usually AI won't make mistake. Next. So having this secret weapon, we are able to produce a way bigger public available data set than other parts, and we can annotate a very diverse class. So here is an illustration. If we want to create such a almost a 10,000 data set, it could have taken 30 years for the radiologist, really hard working radiologist. And using active learning, it can reduce the annotation cost to several weeks. So here is a benefit. And we make it, again, we make it public available. If you are interested in, you can always try and see if it's helpful to your research. Other than organ segmentation, we also care about tumor annotation. So to annotate the tumor is really difficult. The organ probably you can hire medical school students, but the tumor is different. You probably hire expert radiologists, they give you a lot of questions. Do you have a past-proof result or anything? So we try to see if AI, well-trained AI can help to speed this up. So usually people report AI performance, sensitivity, specificity, try to make the balance here 90% and 90% pretty good. But in this scenario, it's changed. We wanted the AI to produce as many as the positive as possible. So here is our Z curve. We want the AI performance not here, but make the sensitivity extremely high to make sure it does not miss any tumor. And of course, you can produce a lot of false positive. A false positive is relatively easy to deal with because we have a radiology report. We know which patient eventually get cancer or not. So false positive for the normal cancer, we can remove at once. And for some false positive, like a random part, the radiologist only have to click less than 5 seconds, can remove it. So this is the philosophy behind our design of the tumor annotation. You ask the radiologist to edit the AI generated label, it probably need 1 minute. And this really happened because AI really did a good job. And if you want to remove false positive less than 5 seconds. So in total, we found using this strategy, we can speed up 80 times faster. With this, we not only public available, we also enlarge our internal data set at Hopkins. So you see now the number is pretty unbelievable now. It's go beyond the big, it's 240,000 patients. And we have the 300 different also vessel and bone, and per voxel annotation. And we also have the per voxel annotation not only to the pancreas tumor. Using this active learning method, we are able to scale up to 16 different type of cancer. And eventually, we really want to deal with all type of cancer to see if we can. Another estimation, if you want to build this big data set, you probably need to hire a very dedicated radiologist to start working on it since 420 BCE. And we did it in 2 years. Last 2 years, we made it. It sounds quite expensive, right? 2 years. You don't want to wait that time to solve a problem. Then next, I will introduce how further we can do to reduce the need for voxel annotation. So you actually have a lot of options. You can have a transfer learning to transfer the knowledge learned from the organ segmentation to detect the cancer. You can also use the radiology report because writing report is actually the major job of the radiologist, not to produce the per voxel annotation. Why not use it? And lastly, synthetic data. We can create a lot of realistic synthetic tumor to consider it as additional training data. Foundation model. So I have been working on foundation model since my PhD. There are two major strategies. First is self-supervised learning. I did it in PhD. It was very popular that time because especially in medical, you don't have a medical imaging app. People have to use the self-supervised learning. And now, since we create such a good base for the organ segmentation, we are trying to see if supervised pre-training also work because it's working in natural image. ImageNet pre-training is a supervised pre-training. So we want to see whether the knowledge from the organ can be efficiently transferred to tumor. Turn out to be yes. Self-supervised learning compared with supervised learning compared with self-supervised learning, it's more efficient because the learning object of the supervised learning is segmentation. And the downstream task we're interested in is segmentation. They are aligned. But self-supervised is different. Usually people use mask image modeling. You remove something and recover. So this do not need annotation, but the goal is different from segmentation. So the study shows, our study shows using the supervisor pre-training from the organ segmentation can dramatically reduce the need for the per voxel annotation for tumor in the downstream task by at least a half. Second, for the report as the weak supervision. As said, the report is different from caption in the internet. Caption, you probably have irrelevant content. I need to work hard, then the picture is a sunny picture. It's irrelevant. But in medical, it's different. The radiologists are paid to write good report, describe the image. So the report is much richer and the alignment is much better than the image caption. So if you check the number, public data set for per voxel annotation image master pair, it may only have 10 or 100 of data before our data set. But differently, report public data have a 500,000 image report page. And we try to see if we can train the AI to use this report text as the text in the report as the weak supervision. And this paper was published in this year, Nikai, and the finalist of a Young Scientific Award and the best paper award.
Sorry, just a quick question. Of those 500,000 reports, how many say there's no tumor?
Tumor, so these data sets are not designed for cancer purpose. So I will guess only 10% have the cancer.
So okay, and so the other 90% just don't give you very much information. Right?
Other disease, other non-cancer disease, for example, bone.
Oh, so they will still describe some anomaly. Yeah, I see.
Yeah.
Okay. And do you have any example of a report on a slide? Like,
Oh, yeah.
I don't know whether it says, oh, it looks like a fish swimming up to the right, or you know, like, what does it say? Great,
Yes.
thanks.
We do have the example for the report, but in this study, we use the quantitative information. So it's much easier. It's a good starting point because radiologists spend the time to measure it. So we use this as a supervision, use the LLM to extract the most important part in this report and incorporate into the loss function. So the loss function will constrain the number of cancer, the number of tumor in this study, and the size of tumor, the diameter, and the location of the tumor. So these are all very relevant information that most people just not use enough. So scaling law, if we incorporate a report supervision into the training purpose, So you can see the gain is a lot, and this is a studies done at UCSF and the JHU data. Report supervision have another important benefit. It can enable us to quickly move on to different type of cancer, right? Because the report is not dedicated to pancreas, for example. It may the radiologist have the have the CT, it may check the whole area of abdomen region. So in the report, we can get a lot of different type of cancer information. So we have internally create a huge database, both the image report pair and the image mask pair to train this. And this really enable us to extend our AI algorithm quickly to different type of cancer. And note that there's no public available data set for this purpose. And we released the first AI algorithm that be able to segment the multi-cancer in the CT scan. Very impressive result achieved. If you do not use a report, you probably just stuck with a limited number of per voxel annotation, 10, 20, not very good. Doctor don't like it. But you get a report, you don't bother the doctor at all, because all the reports are public available, then the improvement is dramatic. Lastly, we try question.
Naive question. So the reports, I guess they're written for the doctors, right?
Yes.
Are there certain conventions on how radiologists communicate the doctors, or is it really free form? Everyone writes differently.
It depends on the hospital and it depends on time. In the previous time, people use free text. That's the reason we need help from the large language model, because you cannot use keyword search or template matching to read the report. Now, for some major hospitals, they have some kind of a template, so that it's a checklist. Then it's much easier for us to read this.
My impression from, at one point I did look at radiology report data, and it was extremely low entropy. Even the manually written reports. I don't know if you've had this also.
Low entropy, I'm trying to translate that. Doesn't have much information.
The number of bits per word was low. Once they say left, you know the next word is going to be lateral.
Oh, I see. Okay. Yeah.
Okay. Next one, next secret weapon is the synthetic data. It's really free now. It's a report still we need to curate. Synthetic data, we can make use of generative AI. So again, the data gap, we don't have enough data to train AI. In this situation, we don't have enough small tumor to train AI, because collecting small tumor, first of all, the radiologists may miss it. So they may hidden somewhere, but we don't know. And the small tumor are 10 or 20 times more common than the late stage. And we care about the detecting small tumor most. So how to, if we cannot get the real world small tumor example, what would be the alternative? Synthetic data will be a very good alternative. We treat the synthetic data as a time machine here, the concept. So let's say you have the very late stage cancer scan, and we want to trace back how this cancer look like in the CT scan. You can use the generative model to generate the image. And you can also move forward. You have a small tumor, and you can create the larger tumor along time. So in this strategy, you can dramatically enrich the training data for one patient. We make it by 2 steps. First, to create how the tumor or vessel or dot will look like in some space, in the pixel space. And we use the algorithm called cellular automata. It's a try to simulate a very complex world using a few predefined rules. Having this, we then use the diffusion model conditioned on the shape create from the cellular automata to render the realistic CT scan from this. And this also enable us to create a different type of cancer. And one common criticize is synthetic data, are they realistic enough? And are they really useful for the AI training? So I can answer the second question easily by doing experiment. They are pretty useful, but first one is quite hard. So we spend the time to create such a test. We call it a visual Turing test to give to the radiologists to ask them whether this tumor are AI generated or it's a real world tumor. And it turned out to be, at the beginning, they are very easy to tell, oh, this is so fake. And we also found this fake data not very useful. And then we get their feedback, say the boundary should look like this, the intensity should look like this. Then eventually we improve the diffusion model, improve the cellular automata. We managed to create very realistic synthetic data for training. And synthetic data is so helpful. If you only use a real tumor data, it's quite expensive to reach the radiologist level performance or even exceed outperform them. But if you can generate a synthetic data, you see the AI performance will have reached the plateau quite at the small early stage. We can reduce the need for the per voxel annotation from 1,500 to only 500. As said, the synthetic data is extremely helpful for the small tumor detection. So with the synthetic data, the most performance boost is from the small data, a small tumor less than 2 centimeters, and the performance improved 5%. And the smallest lesion that we can detect was 2 millimeters. It's extremely small if you look at the visualization, but yeah, it's we can generate a lot of this kind of example for training. That's why in the testing, the AI can be very sensitive.
Yeah, so your reverse time model is derived from just the small set of examples where you have early stage scans as well.
The cellular automata was not a supervised training, so it's a do
No,
not.
that's hand coded.
Encoded.
Yeah.
Amazing it worked, to be honest, in one way.
I mean, I would think there would be a few parameters.
Yeah, it will have some
Right, but you set those by hand, so you got realistic.
Was it?
We do 20 also. Yeah, we do it by hand, also learn from radiologists' feedback, because we are not God. We cannot define this rule really accurately, but we can see if the outcome is meet there.
Right, but the model also includes a diffusion model, right? And so the diffusion model is presumably trained on the cases where you have
A few
you have a few images along the way,
Yes.
at least the start and the end.
Yes.
It's surprisingly only a few are needed for the diffusion, but anyway.
Yeah.
So
Diffusion model, most people want them to generate diverse content in natural image. But in medical, if you look at the tumor, it's just a few dots to you. So they are not very diverse. So that's why training diffusion model in tumor purpose, it do not need a huge amount of data.
Yeah, does it learn anything interesting? Like, the tumor tends to start out and it ends up over here, but it tends to start out in one kind of tissue
Yeah.
and then diffuse along a boundary or avoid a boundary or something.
Yeah, right.
So they're just taking it a bit, but yeah, but still, there's aspect of that. It's,
Okay, so we have a way to make good use of per voxel annotation whenever possible. And we also have a way to enhance the AI using some 3 different weapons and reduce the number of per voxel annotation. Then put them all together, you can get an AI that can deal with not only pancreas cancer, but also different type of cancer. Here, I will briefly talk about the 3 user study that the AI can really help the radiologist to do better and do faster. First is to detect the cancer from the CT scan that they initially miss in the practice when they read, whatever reason. It can be invisible, it can be the radiologist really tired or unhappy day. It can be any problem, but they missed it. And we see if our AI can detect all these cancer earlier enough. So we call it a pre-diagnostic. The definition is you have a diagnostic CT when lab confirm you have a cancer, unfortunately. And before that, you have no idea. So all the 3 years, all the scan you make are pre-diagnostic, meaning they have something probably, and it's radiologist didn't pick up. We tested. Our AI can detect the cancer on our average 8 months earlier than radiologists. Of course, the current, it's just a preliminary data. The current test number of patients are small. I will explain why later. And yeah, we can get it much earlier. And we also want to implement our AI algorithm into the desktop that radiologists are daily using. So we collaborate with NVIDIA and develop this desktop-based and web-based visualization tool to tell radiologists, you know, what's the organ. Of course, they know what's the organ, and to tell them what's the size of organ. This is a headache for them. They need to measure it very difficultly, but we can make it automatic. And more important, we want to highlight the cancer region to reach their attention. And with this software, we are able to really compare the performance between the radiologist and the AI algorithm, compare with radiologist. We pick up a lot of small tumor scan and also the pre-diagnostic scan to retrospectively ask them to re-review all these scans to see if they can find anything, right? And not many studies can do this. So the current, what we know is radiologist for small tumor is very low, but for pre-diagnostic, practically the sensitivity is 0 because they miss everything. But we want to see how much they can do. So eventually in our study, we recruit 30 expert radiologists and maybe general radiologists and radiologist resident to do this study. And they achieve 30% sensitivity and pretty high specificity because they are told to be responsible. They cannot randomly see you have a cancer. So sensitivity is pretty low. And our AI can achieve about double of the sensitivity to compare with the radiologist, while maintain the similar specificity. Second, we want to see whether our AI can help them to write a report, because eventually the product from the radiologist are the report, right? And the two major strategies. One is something called end-to-end. People really love this end-to-end because it's easy. You have input, output, train it done. But this is not very working, and so we proposed a second solution. First, segment it, then report it, to be able to be sure the report is grounded by the real observation. Why end-to-end vision language model not working at the moment? Because it's good, it's end-to-end, but it will have a hallucination. And it happens a lot. The problem is you don't know how to diagnose it, because usually the language model is released and you don't know where it can go wrong. So the example of the automatic report generation will first based on clip, then based on some other follow-up work from different research groups. It's understandable because they do not have a provoxel annotation to train. End-to-end is only choice, right? So end-to-end means you give a CT, so big CT, you want to localize 0.0001 tumor from this CT, then get a report this accurate is a very difficult job. Since we have a provoxel annotation and we have a segmentation model, we can first segment it, segment the organ and segment the vessel around it and to segment the tumor. And then we can really, based on this segmentation, to generate some deterministic algorithm. We don't even need a large language model. We can just produce accurate report automatically without any GPU, right? And it turned out to be very end-to-end it's here, it's a baseline. They're not very reliable. So most of the time, small tumor, yeah, missed everything. And larger tumor performs not very good. So basically the reporter just imagine something, right? And our segmentation then reporting approach can achieve very robust performance in this report. That's the most important part for the doctor. And here's the example how our generative report will look like. It's actually a superhuman report. It's not just a random radiology report, because radiology report, it might give you some basic information here, and they, most of the time, they don't measure the volume, because measure volume is, you think about it, it's very time consuming, especially you don't know the boundary of the organ or the tumor. Then why it's a superhuman? First, we can do a lot of things the doctor want to do, but too tedious, they don't want to do, right? And the second, we can visualize this CT scan and make a contour what our AI generated report is based on. So this have the contour of the tumor and so on. So this not happen in the radiology reporting practice. It's basically a screenshot of the CT and the annotation.
I guess to address Jason, you can adjust the entropy if you like.
Yeah, and the radiologist can edit based on this initial report.
Yeah, stuff can be removed.
Yeah, I have no opinion about how people should write the reports. I was just saying that they did write them in 2005.
They should be standardized. Some of them are standardizing, I guess, which is good. Otherwise, yeah.
Last product from us is the LLM enabled CT retrieval. So conventionally, if you want to do a cancer related study or you want to do some good study, you want a radiologist to help you prepare the data, the suitable data, whether it's a positive or negative. And if you want to do longitudinal study, you want them to prepare this for you. It's extremely time consuming again. Radiologists may need 15 minutes to go into the database and click a lot of buttons to give you the right scan. And using LLM, it can make it less than 5 seconds. And if you have a better computer, you can make it even faster. So why is this important? Because we find it's really extremely helpful for the pre-diagnostic study. So think about it. If you want to do this study, we have a database having 400,000 patient records there. And how to read first, get all the relative data for you, the pancreatic tumor, for example, and how to trace back time to see whether the report really did not mention anything or it's mentioned something similar, but not exactly the word. We all need a large language model to read it and analyze it. And eventually, I think, surprising, we only get around 1,000 really useful data for you to do this study. And this is a purely searched by large language model. And then we have the human verifier to screen out all the hallucination from the language model. Then eventually the number of useful study go down to very small number. So 500 out of 400,000 study. So this really, the LLM-based retrieval really open a door of many different research topics. First, straightforward, you can build a bigger data set. You can make use of all the data from the entire hospital or entire even country, right? So we are planning to use this same strategy to create even bigger data set, even private or public available. We can also use the same algorithm to build a multimodal question.
So on the previous slide, how do you check for false negative when the language model will not pick up what it's supposed to pick?
False now we can't.
Okay.
Yeah, so here it's all candidate. If a language model missed it, we miss it.
But it could be the most important report that you need.
Yeah.
Would you say
Yeah, so the question is, what if the language model missed this part and there's no human verifier? So Yeah.
You're checking these, people are checking that up.
Yeah, that's this stage, so.
Oh,
we
the two-way
have-
validation, so there's humans checking it afterwards.
Yeah, so we study why we miss cancer. We have a Center for Diagnostic Excellence at Johns Hopkins Hospital, which is a designated center to study that specifically, funded by the federal government to do that. And we found that if we look at cancer diagnosis and when we miss it, if we want to move the needle to help patients, the core two problems that happens across the entire life cycle of diagnosing cancer is that we never order the image that was supposed to be ordered in the first place. It's a reasoning problem. And then when it was ordered and the report was produced, the report was not used on time, or it was not understood well by the physician, not the radiologist. And those were the two bottlenecks of detecting cancer early. In fact, we just did an analysis for the NIH. We found that we missed 35% of all lung cancer cases in the National Lung Cancer Screening Trial because the report was not actionalized. So there was no follow-up decision to actually who should we biopsy based on that report.
Yeah.
So, and then when you get patients to progress with their case, and then you have to go back to try to diagnose them, you need to retrieve the most important image or a report that could help you take action. If you miss it, you will break the entire chain, and then that patient will be missed, and then they will show up with stage 4 at some point. Right. And it will be too obvious, and then it will be predicting the predictable. There is not much benefit to the patient.
But that sounds like a systematic error.
It is a systematic
I
error.
mean, and it sounds at the moment that even if some way can get things working at 100%, it may not help with the system will not working. But but one thing I guess, at least I found from the side is, if you start getting AI into it, it means you start organizing things, and so you can use it to, in these collaborations here with the UCSF, you're able to use it to find these things and sort of organize and make things systematic, and you could flag cases like that. If you don't have the data organized in that sort of type of way, then it's really hard. I mean, I've worked with people in Hopkins Hospital, I know the data there is not organized nearly as well as the data from my UCSF collaborators, which is used in some of this work.
I think if we want to realize the benefit of AI in a clinical decision making, that will truly improve survivorship for patients by shifting the diagnosis from stage 4, let's say, to stage 1. You need to fix the part just prior to taking the decision to say this patient deserves an image. We need to do that image, whether it's a CT, MRI, or anything. So that's the part that will yield the highest benefit to patients. If we can fix that part, then we will reach the image, and then AI, even if it's 90, not 100%, if you can really scan everyone that deserves to be scanned, even at 90% accuracy, you will benefit the system substantially.
I mean, I can see this as a big problem that we haven't dealt with, but at the same time, surely one of the big problems is the performance of the radiologists on this. And
Yes.
I don't want to knock them. It's a really hard thing to do. It's extremely unnatural, and it's a lot easier for AI because AI can see in 3D. But it seems that there are big progresses that can be made here. But you're saying unless it's combined with the organization structure progress,
You will not realize patient benefits.
you won't.
Yeah.
But at the same time, the AI, when it's organized like it is at places other than Hopkins, not many of them, would make it a lot easier to do that than it is here.
Yeah.
From everything I hear from collaborators and people at JHU.
Also, deciding which patients to image can also be treated as a machine learning problem, right? It's not the problem that they're dealing
So
with.
we are using LLM for that. We're using other traditional machine learning for that.
Well, we are doing some of that.
Yeah.
There, because we've got the data, you can try and see how good the business
Development part
factors
of
are.
diagnosis.
You can analyze it with AI too, and you're saying you're doing that also. Yeah. So it is machine learning. Formulating everything as an AI or machine learning problem, I think, it's got huge benefits beyond the things we're saying here. Yep.
Right, correct. So actually, we have an action item here to use the better algorithm to monitor, because you are able to get the paired data, the longitudinal data, and you can read the report automatically. You can somehow pick up all these risk factors, whether the patient is worth to take a picture or not. And the last, we want to use this efficient technique to be able to expand to different type of cancer. And we just another topic is CT itself is limited because 1 pixel maybe it's the 2 millimeter probably is the smallest thing we can detect from the CT itself. So we try to make the CT higher resolution to be able to visualize better for the small tumor. So this is actually my main focus on the R1 grant. To be able to retrieve all this data, including creating the full voxel annotation, and to be able to treat the patient better along the different timeline, so that we can simulate what this patient will be react to different kind of treatment plan without really hurt him. Then, probably this patient will be better cared in the practice. Yeah, so it's like we got the time stone. We are able to see all the possible future for the different treatment, and one possibility probably lead you to get better for the cancer. So the last I want to say, AI really we show evidence AI can make a positive impact to 2 type of tasks that we are focused on. First, the task is the radiologist can do very well, but they don't want to do it every day. It's tedious, it's a low value, right? You want the AI to jump in to make it faster and reduce their time to focus on more important tasks. And the second task is the radiologist really want to do well, but they can't, maybe because of many reasons. And for example, early cancer detection or write a very accurate report in a small short of time. And with this in mind, my research have always been focused on the combination of 2. I cannot leave one behind because you create novel algorithm is not useful, it's meaningless. And we got the application to have the touchstone of all these algorithms to see whether it's really helpful or not. So in this talk, I just cover all the research topic I have been working on in these years. And these have been published in both AI machine learning conference and clinical conference. Thank you very much for your time. I'm happy.
So we went slightly over time, but that's fine. So other questions? I mean, we had a lot of questions, but yeah, go ahead.
Sort of a curiosity question, when you're doing, say, the labeling, are you doing like per image in a 2D or in 3D?
3D.
Oh, you're linking like between 2 slides and so, or you do the regression.
Slide by slide. You have a 3D CT in the volume, then you annotate this slide, annotate this slide, slide by slide. Then eventually become a 3D annotation.
Sort of a dumb part, it's kind of like all tumors are in 3D and they don't really align with, say, you have a lab corner or an image corner. Even for the pancreas, it's always aligned the same. You know which axis the lung is at. But if the tumor is in the biodata of the pancreas tail, the shape will be different. I'm not a radiologist, but when I took radiology, I was trained to, at least my teacher told me, it's like we just scroll through the entire sequence. So I sort of picture as I was thinking in 3D. I know it's like when I see something, I sort of probably imagine what an organ functions. If I see like a different lane, now I realize the part's probably different. But for sort of like I look at the sequences, like I would start to picture where is the first site I could see the tumor. Would a computer be able to do that work?
But the computer can do better. That's one reason the computer is better. The computer accesses the 3D information directly, whereas the human just has to look at slide. So that's one reason the AI is so much better. It's becoming finished for humans. We don't need to do that. The computer doesn't do that, humans do. And also humans haven't evolved into these things, and the AI can now see far more CT scans. So that's
Yeah, the algorithm takes the 3D CT directly, so human just see it from 2D screen, so that's a difference.
Yeah, X-ray vision like Superman.
I wonder if I can ask one last question.
Sure.
Sort of like, I wonder if the patient pool is more like an adult, so that the organs they have similar size, or if you can deal with like childs or pregnant women.
Oh, childs, many people mention childs to me. I haven't got any data from that. But yeah, it's always good to test it. It's a very out of distribution. I don't know. Yeah, if you got any good data, we can first test them.
But fortunately, these things are not so common.
In China, yeah, you know,
With people your age, they're more common with people my age. But yeah, these things have, the data sets have age in them. That knowledge is available in the risk factors. You know, age is one of the risk factors for these things, so. Question?
Project where you are using the radiology reports, how do you know that the reports are correct? Is there a way of knowing?
we don't know. So that's why we have some tolerance. So for example, radiologist report says a 2.3 millimeter. Yeah, so AI predicted some certain range we will consider as correct. Because even you ask two doctors to read it, the number will be different.
Dr. Human.
A more of a philosophical question. You can feel free to we can talk about it after, but I think like in 2016, Jeffrey Hinton said like we should stop training radiologists. They're gonna not have a job in 5 years. Obviously, that's not the case, but something like this strikes me as like it'd be great in training a radiologist to be better. What do you think?
Yeah, we build some software to give them the first read for the AI. It's not necessarily correct, but hopefully it saves their time to faster localize the area. So the difficult part is how to embed into their system. The difficult part is not AI algorithm. AI algorithm improve every day, but to be able to embed in their system, their GPU may not be good and every limitation, the privacy limitation. So that's something we try to figure out with some hospital first to let us test because this is not FDA approved. So have us test for the previous scan first, then to see get more evidence, confidence it will work.
Makes sense. I mean, I think if radiologists are working with these things, then they, you know, and when they know these things starting to look better, it's just going to make them better.
I think it's like a project three. I just didn't really understand the graphs at the end. So I remember it was the natural, you were using LLMs to understand what the radiologist had written, right? And then there was a reduction in like the need for something, but I couldn't understand what based on the graph, like is the pink and gray graph? Like there's a bunch of bar charts. Yeah, that.
Oh, this one just the comparison. You train AI with the report, or you train AI without the report.
What were you training AI on and to do in this case?
Oh, tumor segmentation.
Well, to detect and segment the
The
tumor.
tumor from.
Oh, so you're trying to detect if there's a tumor, but then you have the report that says there is a tumor.
Yeah.
Well, before then you had, there's a few examples, there's a few seeded examples.
Yeah, so the training is like this. You have an image and you have a report, and you train this AI algorithm. If the AI algorithm prediction align with what the report they describe, then it's good. Otherwise, give a penalty during the training. And in the testing, the AI can segment this.
Go back, I think, I thought it was slightly different.
Go back to
The slide, the graph.
this.
Without the report, it was trained with something. Was that? It's trained with a few annotated, if I'm sure, remembering it's trained with a few annotated, but not many. A very few. And then if you combine the report, then you can, the report gives you extra information, it is more weak. And and translating, and then it gets a lot better.
Yeah.
So you don't need to annotate 5,000 whatever things in the spleen or something, you can annotate only a few. And then you can, yeah, report then can take you a lot further.
So this is an argument for the combination of using like a text understanding LLM alongside segmentation for
Yeah,
training.
Along
learning.
with the segmentation, because that did take people 25 person years, and it was not fun for them doing it, I know.
But you already have a segmentation algorithm.
or
Well,
if we do
sure.
different type of cancer, you see, or other disease. So this is Felix spent a long time to do the pancreas only, but if we want to extend to different organ to reach the radiology performance, we need something new.
Well, and also we want the results to be better on the pancreas without making these people change them into office and 5 hours of time and taking them. I don't need to. It's, trust me, the people who did that, I knew them, they did not even enjoy it. It's very boring thing to do. And so maybe a few people do it with some sort of active learning thing, and then you can rely on the reports, because anyway, when you've got the LLMs to get that information out.
Right.
So we're trying to, try to reduce the need of human slaves.
That makes sense. And your last, sorry, one more question is your last section is basically, you're trying to use LLMs to create more data sets in the future. Is that sort of the idea?
Create more like a search or organize the data in a AI ready manner, so you can start develop the AI.
But that only works once you've already got, because I was thinking on the hospital end, like the issue, you couldn't have had a search like that because the whole issue is privacy anyway, so.
What we did is download everything to the disk and then from it. We cannot directly move the LLM to the assistant.
There's privacy issues, so some universities or hospitals have got their act together. Hopkins isn't one of them. They're working on that. They've been working on that since DSA got invented. So they may get their data organized. Then there was a privacy, they're trying that, but then some people, these exact people got their act together. So it's in a form you can use to run the algorithm, it's a collaboration and get all the stuff. Hopkins you could imagine. Well, how long have you been with Hopkins?
No, I have in Canada, data privacy is worse there, like you can't access anything in the hospitals basically, so I'm just like the systems are archaic.
They are, I mean, but some are a lot less archaic than others. I mean, they are working on it, they realize the importance of it. I mean, it seemed all the issues that guy was bringing up, right, that's a system problem. If the data is organized properly, previously you had to deal with them, that sort of thing wouldn't happen, or if it did happen, you could check. You can check if you could keep track.
Yeah.
I think at the moment, there's nothing to keep track of how good a radiologist is. In the rational world, and see what predictions they make, how well they've gone up. It's a data organized, you can do that. I mean, you have to keep that far too, not very business, but I mean. All right, that's going fine. Are there other people, I guess there are people online, but anyone raised?
I don't see a question online.
Your talk was so clear. Okay, well, in that case, I think, thank you very much.